let's identify where we have vertical asymptotes. So let's identify when is the denominator equal to 0. Now, in this function, our denominator, it's a trinomial. X squared plus x equals to 6. Now let's set this equals to 0 to identify the location. Let's try to factor this out. Let's look for two numbers that if we multiply, it gets me negative 6. And if we add them up, it gets me 1. Well, those two values is 3 and negative 2. Let's confirm that. 3 times negative 2, that gives me negative 6. And 3 plus negative 2, that does give me 1. So now let's factor this out. Instead of writing the whole expression as x squared plus x minus 6, I'm going to write this down as x plus 3 using the first value in our combination and x minus 2 using the second value in our combination. And now we can identify the value of x's that we are looking for. Let's set the first factor equal to 0, and let's set our second factor equals to 0. When we solve for x in our first factor, we identify the location of negative 3. When we solve for x in our second factor, we have the location at positive 2. So there are two values that make my denominator equal to 0. So we should expect to have two vertical asymptotes. Let's say that positive 2 was about here. So let's draw a vertical dash line. And let's say that negative 3, it's somewhere around here. Let's draw a vertical dash line. Now let's graph this function and let's see if this is true. So here we have the graph of our example. Now let's draw the line of x equals 2. And when we take a look at the behavior of our function, notice that the graph itself, it doesn't seem to be using this x value. It is kind of like a wall. We have confirmed that it's a vertical asymptote. Now let's graph the line of x equals negative 3, which we have it here. And we have the same behavior. Notice that our graph, which is displayed in red, it doesn't seem to be using this x value. This vertical line, it is some kind of a wall. We have confirmed our conclusion. The function that we're given, it has two vertical asymptotes at x equals 2 and also at x equals negative 3. Let's take a look at our last example. So we have the same objective. Let's try to identify the vertical lines. But notice that we have almost the same example. The only thing that is different in this example is that I have changed the numerator to x plus 3. Well, let's try to approach it the same way. If I want to identify vertical asymptotes, let's try to see when is the denominator equal to 0. But previously, we have shown that we can factor this out. For the denominator, we were able to factor it out as x plus 3 and x minus 2. So if we just follow the same strategy as we have been doing, maybe we are going to say that we have two vertical asymptotes. One at x equals negative 3, and another one at x equals positive 2. Because those are the two values that will make our denominator equal to 0. But notice that we have not simplified this expression. When I consider the whole rational function, the expression of x plus 3, it is going to cancel with one of the expression of x plus 3 in the denominator. So really, the function that we will consider is just 1 divided by x minus 2. So it is not true that we have two vertical asymptotes, but we only have the vertical asymptote at x equals positive 2, because that is what is left after the simplification. So let's show this. Let's say that 2 is in here. So this expression that got canceled out, we will not consider as a vertical asymptote. But we cannot just ignore that we were not able to use the value of x equals negative 3. That was a value that we were not able to use on the original function. But because it got canceled out along the process of simplification, we are going to refer to this as a removable discontinuity. At the value of x that we eliminated when we were simplifying our rational function. And the way that we're going to represent a removable discontinuity, it is not but a vertical line or any line whatsoever. This is what we refer to as a hole in the graph. So let's visualize this and graph our function. So when we graph the function that we are given, right away, we can see that we do not have a vertical asymptote at x equals -3. But we still have it at +2. So let's keep that in there. We can consider this as the graph of the function. But there's one thing that we need to include in this graph. We have said that x equals -3. It's a removable discontinuity. It got canceled out when we were simplifying. So we have to represent this as a hole in the graph. X equals -3. It's in this location. So whenever our graph it's passing through this x value, well, let's just draw a hole in it to show that we are still not allowed to use this x value, but it is not a vertical asymptote. It is what we define as a removable discontinuity. We cannot forget that at the original function that we were given, we cannot use the value of -3, and we cannot use the value of +2. They still make our denominator equal to 0. Hello. If you would like to continue learning about mathematics, you can check out the videos on the left.